Okay, so let's work through these worksheets and see if we can do some reactions. So in this first type of reaction, the first thing that I'm going to notice is that we have an OH here. Well, OH is a base. And this is literally called a carboxylic acid, this functional group is. Don't pay attention to what's over here. It doesn't really matter what's over there. This base has lone pair of electrons, and they will come like Pac-Man and come over here and grab this hydrogen, and together they'll make water. So all you all need to really realize is that the hydrogen is coming off, and that leaves behind an O with a negative charge. The same way this has a negative charge, when it steals a hydrogen, it leaves behind a negative charge. And there's electrons, if that's helpful. So in this case, we're reacting with a base, so this is simply a base reaction. The next one, we're dealing with NH2. Well, remember, NH2 has a lone pair of electrons, and sorry, this ends up looking a little bit funky. What it really was supposed to say is that we have H3O+. You could also see H3O+ as H+, sometimes written up that way, or H2SO4. All of these things really, once they're combined with water, which what acid has to be in anyway, is H3O+. So we have an acid, we have nitrogen. So nitrogen or amines are basic, and they will come and grab the hydrogen over here. So we come and grab a hydrogen, and we end up with, these stay the same, we end up with an NH3. So we have 3 different hydrogens there, and the positive charge is on that nitrogen. So this would be an acid reaction. Okay, let me move this on down, and let's keep going. Next, we have what's known as reduction reactions. It literally tells you in the problem. So this is a reduction reaction. If we start with a carboxylic acid, the first step of reduction would be to reduce the amount of carbon-oxygen bonds. And so what we would end up with is an aldehyde. Now remember, with aldehydes, you can put the hydrogen there, you cannot put the hydrogen there. It doesn't really matter. Either of those is the same thing. We can continue a reduction here by reducing the amount of carbon-oxygen bonds. And so you can end up next with an alcohol. Now it doesn't matter if you draw it like that or if you draw it like this, whatever is totally fine there. Next we come to this reaction. It looks like an alien is trying to land. But in truth, what this is we're combining some type of carbon hydrogen species with oxygen gas. Well, if you remember, that's just a combustion reaction. So that's the type of reaction we have here. It's a combustion reaction. And so you don't even need to, figure out what the stoichiometry is here or balance it. Just realize that that is a CO2 plus H2O plus energy. Okay? That's all that reaction really is. Next, we have hydrogen that is added across a CC double bond, because that's our only functional group. So that's where the hydrogen must go. So if we're adding hydrogen, we refer to this as a hydrogenation. Okay, so remember, this CC bond is really a CC. And if we're adding hydrogen to it, sorry, I ran out of room, let me go over here. We're gonna have a CC single bond with extra hydrogens that are added, right? Because that's her hydrogen right there. Well, when you go to write that in skeletal structure, you may not actually see the hydrogens at all. So it looks like they just disappeared. But in truth, they're totally there. So just remember that. Okay, next, this little O up here tells you that we're going to do an oxidation reaction. And that means we need, at least in organic chemistry, the easiest way to look at that is that we're going to have more bonds between carbon and oxygen. So in the first step, what we're going to have is simply a CC double bond like that, or CO double bond, excuse me. So here's the thing. When you get to this point, this carbon already has 4 bonds to things that are not hydrogen. So it's 4 bonds to either another carbon or another oxygen. And so he's done. He can't do any more bonds. He can't make any more. So we say that in this case, on further oxidation, there's just simply no reaction. Now, I simplify that to say no RXN, but that's the same thing as saying reaction. Okay. So let's look at a few more, a couple more here. Now, the next reaction is using acid, because H2SO4, that's all it is it's saying, hey, we've got some H plus here, or H3O plus, because we can call all of those things acid. We're using an acid catalyzed, and then we're adding water. So we're doing a hydration. So you could call this a hydration, or you could even call it an addition reaction. That's fine with me. Whenever we're adding H2O, we're adding an OH and an H. So what happens is that this bond in between here is like, it goes away, and we add new bonds here and here to different carbons. So the thing is, we have to then decide who gets the OH and who gets the H. Well, first of all, let me just kind of erase the fact that that even happens, just to simplify life a little bit better, because that way it doesn't get as confusing. Remember, there's this thing called Markovnikov's rule. Long and short of it is the OH goes to the most substituted carbon, the carbon that has the most bonds. Or the most bonds to other carbons. That's the easiest way to do it. So this carbon has 2 bonds next to it, and this one only has 1. So that means that this guy is who gets the OH. So here we go. There you have an OH. Well, you might ask, like, what happened to the hydrogen from the water? We still need that too, right? Well, keep in mind, yes, it's absolutely right there. But when we draw things in skeletal structures, you can't see hydrogen, so it looks like he's not there at all. Okay. And again, sorry about this. Don't know why, but it didn't translate very well. Okay. So if we have H3O plus, and we've got an amine, remember there's still a lone pair of electrons there. An H3O plus, or an acid, just simply attaches itself to that nitrogen. So we'll end up with those 2 carbons still there, and then we get 2 more hydrogen that are attached, and you get a positive charge. So that's simply an acid reaction, or an acid-base reaction. Okay, we're moving along, guys. You're doing great. So next, we're going to add some oxygens to some stuff. Well, that's called oxidation. I guess I changed colors on us, huh? If we oxidize, we're increasing the number of carbon-oxygen bonds. And the first way to do that for an alcohol is to make an aldehyde. Now, we do have another carbon-hydrogen bond that we can extend here, and we can end up making a carboxylic acid. If you drew that in a different way, like this guy, hey, that's the same answer. That's totally fine. Same thing over here. It's completely fine. If you wanted to put the hydrogen on that aldehyde, you go for that. It's completely fine. Don't worry about it. Okay, next. This one might be a little bit harder to see. But what we're doing is we're going to form an ester. So remember how these two things come apart and make water. Okay, well, if those make water, yeah, you can write this here. You could not write that there. I'm fine with either one. But the point is to me, that this oxygen and this carbon are now going to be attached to one another. So let's draw that product. We have the two carbons, 1, 2, from right there, from that alcohol, and there goes our oxygen. He's still there. We're now going to connect him to where that C carbonyl bond is, or the C double O bond. Remember, that's a carbonyl. And then put the other stuff out here. So let me highlight that for you. This bond right here, that's the new one. That's this guy. Okay. That's what I want to make sure that you see is there. Okay. Now, what type of reaction is this? Yeah, you can say that it's an esterification because you're making an ester. Fine. If you also wanted to call it a dehydration, that's fine by me too. The next problem on this worksheet, I don't know what I was thinking. Let's move on. Okay, let's go to the next one. We're going to do the opposite of what we just did. Now, there's no water that's listed here by itself, but if you have H3O+, you have water. So all we're going to do is we're going to separate this bond right here and make sure that we add an OH to one side and an H to the other. And that's where the water is used. So technically this is a hydration reaction. Okay. So in this case, we're going to get an OH and 2, 3, and there we go. So you can make esters and you can break esters. That's how we do those. Okay. The next question, move the box. Just to give you a harder time, huh? Well, let's think about what we have as a product. See right here, we have H2 as a product. And we have a double bond, right? Well, chances are what that means is that we've lost H2 because we had hydrogen on the other side. So in other words, this is kind of just the opposite. And we started with an alkane. Let me translate that for you. We are taking off the hydrogen from here and from here. That gives us the H2. And in losing those two, that's how we end up with this double bond right there. So this would be a dehydrogenation or an elimination reaction. Either one of those is totally fine. Okay. Next, we actually have two here in a row, here and down. I'm going to skip down here, that are amides. We have an amide, and we are going to break apart that amide, just as we did before. If we have H3O+, we have water, so you can assume that in either case. Now, remember, when we do amides, we first have to take them apart, and then we take into account whether or not we're in acid or base, which means that the answer here and the answer here really start off to be the exact same thing because they're the same molecule. Okay, so that means, and I did flip this in comparison to my notes, so be aware of that, that I would have this and the carboxylic acid would be right here. okay? Because remember, when you break this bond, the OH from water goes to the COOH, and the hydrogen goes here. That was originally the water that we are adding from right there, okay? Same exact thing would happen down here. And then, and only then, do you take into account the fact that you're an acid or base. So, I'm going to do that one in blue. Let's now take into account that this is acid. By doing that, I mean I have to take off those electrons up there because now I've got to put in another hydrogen. And when I'm in a base, I need to remove that hydrogen down below because acids and bases react together. And I end up with a negative charge right there. Okay, so they're the same except for the fact that you have to then take into account that you're in an acid or a base. Okay. So this would both of these would be a hydrolysis. This would be an acid hydrolysis. And this would be a base hydrolysis. Okay. That leaves us with perhaps the most difficult, or one of the more difficult. We have an alcohol, and we're adding heat in the presence of an acid. Well, remember, an alcohol with heat and acid causes a dehydration to happen. What that means is that this OH is going to pair up with the hydrogen somewhere and make a double bond. Now, this OH is connected to this carbon right here, right? So it can only take a hydrogen from one of its next door neighbor carbons. So it could take one from over here, or it can take one from over here. So you know how there's one there, there's one right here. Okay, I'm drawing them completely not like I normally would, but we'll go with it for now. So you have to decide which direction you're going to go. And the way it turns out with Zaitsev's rule, you've got to select the hydrogen on the carbon that has the most substituents. So it's going to be this one. And these come away. So in other words, the carbon that has the most friends around him, that's the one that's going to come off. And that's where your double bond is going to run. Like that. So this would be a dehydration reaction. And that is it, you all. I would definitely encourage you to repeat this a few times and see if that is helpful. Good luck.